All right, good morning, everybody. I'm happy to see so many faces in the morning at 8:15. I was wondering whether we are going to outnumber the audience. So this is really nice. Thank you very much. So we have a long title, but a lot of content to cover also. So this will talk about the SDM and tiered memory. And we'll start with the hyperscale infrastructure. Reddy is with me from Intel, and I'm from Meta. So let me get started on this discussion. We have agenda to cover. We'll start with what memory challenges that we see in hyperscale infrastructure, specifically what use cases, why we were interested in it, why we need this software-defined memory, what is software-defined memory, what we are doing to look at those problems and how we can solve those, what specific use cases that we see that need and what their requirements are, and how can we really make sure that we can deliver for satisfying those needs. And then really, this is more of a setup for telling why we are doing it. The how part is really the important large part that Reddy is going to cover, which is going to how this SDM is being enabled for the next generation processor, and general overall software infrastructure that is required and is being growing now for software-defined memory. We'll touch upon also what work is being done in the industry, how we're trying to enable it, and then explore how we can really engage larger community to solve these problems as we get into this journey for memory that is next generation, and how we can work together to solve the problems. Let me start with the hyperscale infrastructure, specifically taking from Meta, setting up the infrastructure, reason why we think this is important problem to solve right now. As you can see, for Meta, most of the applications that you will see in front end, whether it's Facebook or Instagram or WhatsApp, Messenger, all these applications rely significantly on the infrastructure on the back end. As we keep on adding more users, more data gets uploaded, more data gets accessed. There are expectations of the continually growing performance for the applications that it needs. It relies on the back-end infrastructure where we are running lots of databases. There is a huge amount of data warehouse data that is being put there. The training and inference infrastructure that continues to grow fast. All of this really depends on the infrastructure on the back end that is growing, which includes all the system components, whether it's compute, whether it is memory, whether it is networking. For today, we'll focus on memory, but all this infrastructure growth to get the performance at the efficiency that we need from TCO perspective is crucial to make sure that we have the right solutions being developed on the right options that are provided for these applications. Today, we'll focus on memory part of the challenge as we see in the infrastructure. Memory is a significant part of the TCO math on our infrastructure. And as we see how the memory is growing, you can see that the density for the memory continues to grow, but not necessarily bandwidth grows in line with that. What this means is the applications have to make choices. When I need capacity, essentially I'm going to continue to add more DRAM DIMMs, which may add more bandwidth. But if I need more bandwidth, but not necessarily capacity, I have the same choice. I just have to keep on adding DIMMs. CPU and DRAM are tied together so far, which basically means when I go to next generation, I have to go on to that next generation, which will come with its own opportunities as well as challenges. So the gap between the bandwidth and capacity, as we see increasing density on the DIMMs as the process density continues to grow, this gap is widening, which basically means we have to make sure that the challenges for the SKU definition is the hardware SKU definition is much larger, because now we have an opportunity to make sure that we can continue to get the maximum out of the CPU, but to achieve the max performance, the DRAM has to grow also, which is perhaps in capacity bandwidth, but you get one or the other, which basically means you will end up stranding something, which leads into the gap that applications typically are ready to make some trade-offs, where I can say, hey, I'm ready to live with more bandwidth, I'm ready to trade off some bandwidth for achieving higher capacity and vice versa. Those choices become less if you have only one choice that I can put this type of memory. The power also continues to be a significant part. If you look at the overall pie chart of how much power we spend on the performance, DRAM contributes significantly. And as we see for the next generation, the power is growing. As we add more ECC, etc., our power for the DIMMs are going to continue to grow. If that's my only choice. Again, if I have to balance power of the platform, power is a very important aspect for how we deploy the infrastructure. Our power, most of the time, deployment is counted also in terms of power, how much we're adding, not only the cost. The power is a significant factor here. Again, applications are becoming much more aware of their needs because that's an important factor. And so they need choice. They need to have a choice of saying that how much bandwidth I need, how much kind of capacity I need, and can I do any kind of a tiering to achieve the most efficient design that we can do to achieve lowest stranding. Because this is what TCO is driven. Anytime you have stranding of capacity, whether it is a CPU, whether it is a DRAM, whether it's a network bandwidth, whether it's storage, in a different varying ratio, it has an impact on overall cost, overall power. CPU and DRAM contribute significant part of it, and in the storage platforms, of course, storage components contribute most of it. So the DRAM definitely is something that is important for us to have a choice of trade-off so that applications can make the decision. What do they need? Do they need capacity? Do they need bandwidth? And how will they tier that capacity appropriately for achieving the performance that they need and the capacity that they need? So this is a challenge today because we have one option, which is for a given processor, you can add this kind of, once processor moves to DDR5, I'm going to go to DDR5, to DDR6, and those densities will continue to grow along with the processing density. So there is less of a choice today that allows applications to do the compromise or write trade-offs. Let's map it into the applications from a traditional pyramid that we have seen from the storage side. This is more looking from the similar pyramid from memory side. So you have the highest performance in the top, and then you have the lowest, highest capacity at the bottom. And then applications will go across those. I mean, here I'm talking about NAND SSD really as a more of a memory expansion technology, not necessarily storage insert. So all of these are looking from storage as more of an ephemeral storage, if you will, not a persistent storage. So traditionally, highest performance, whether you consider the cache lines or high bandwidth memory, this is something that you will see most in the training workloads, or even some for general purpose compute, which is driven by the CPU performance, but they need memory bandwidth to keep up to make sure that the data is fed at high bandwidth. So you'll see this top tier is typically driven by general purpose compute training or inference and caching kind of solution, because caching is also like a storage platforms. It's just that it's ephemeral storage. So the data needs to be there for a certain amount of time. So memory is treated as a storage. Only thing is the duration is pretty smaller as compared to the persistent storage. Availability expectations are different. But this is where you will see most of the high performance applications sitting, which are more in this area. And then you have applications which continue to grow, database or even some kind of a caching applications which require memory to make sure that we can keep enough storage capacity on the node. So that's what we need more memory for that. So this is the typical pyramid today. So as you can see, this is pretty large, but also pretty fixed. There's not much you can do about that. You have a choice of going from DRAM to NAND, and the gap is significantly high. You are going to uncached accesses across PCIe, which basically means applications need to be able to change and adapt to that, which is a significant change to the applications. And also, we'll talk about that a little bit later, which has an impact on performance also. Anytime there is an impact on the performance, which means in the fleet, you have to make a decision of adding more capacity to trade off, to make up for that performance gap, which leads to higher power, which leads to higher TCO expenses. So this is where I think we need the software-defined memory. We need optionality on the memory. What kind of memories we are putting, what capacity, what bandwidth, and how applications can take advantage of those different technologies to make the most optimal solution to stand the least. And this is where now CXL comes into picture. CXL is now the new industry technology that's going to be enabling memory connectivity to CPU. This is where first time we start decoupling memory from CPU complex itself for the direct attach. The number of channels that you can land on a CPU are going to be bound by the how many pins and how many capacity that a CPU can support. And when performance and bandwidth performance as well as capacity needs grow beyond that, CXL, of course, is going to provide you option for extending. Sometimes you'll get maybe even before you run out of the channels. So this is the first time you'll see the cache coherent interconnect that comes out of processors so that we can have memory expansion. This is the reason why this is now starts to be driven by the emerging workloads that are going to be drive for faster data processing, which is actually more of a bandwidth need. You'll also see the applications which are going to be capacity as well as bandwidth, or sometimes capacity where we are ready to trade off for bandwidth. There have been multiple solutions. There were multiple solutions. Now they are converging. There were multiple solutions that were evolving for this standard for extending the memory. You have seen it in the industry for last many years. Now that all converging to CXL that if you have seen announcements in the last few years, which will allow you now to go beyond the one option that we have, which is DDR. And now you're going to get, say, different types of technologies. You can have a CXL device which can host different types of memory behind it. It could be different technology. You can have DDR5 on the processor, but you can have a DDR4 sitting behind DDR4, behind CXL switch, CXL device. There could be different technology. There could be SCM or storage class memory solutions that will continue to emerge, which are going to let you have a right choice of how much capacity we need and trade-offs. Yes?
Well, I can see with the SCM being attached, it's not on the processor, but isn't HBM sort of necessarily right next to the processor because of the bandwidth requirement?
That is correct. That is correct. Yes, you are absolutely right. I mean, we don't know exactly how it can connect it. Essentially, that's what we are saying. But you're right. Actually, the performance needs for HBM are such that you're going to see it right close to the GPU rather than sitting behind another bottleneck, for sure. What we are saying is basically you can have now different types of technology. It's not. It's really disconnecting those things. You have CXL in the front and different types of technology of memory behind it. There could be a CXL switch where you can go across and then have multiple devices sharing and pooling technology. This is something that's happening. CXL 3.0 was announced recently in August, if you have watched that, which allows you to really have much more hierarchical solutions for memory expansion. So what we are seeing is that this is where hierarchical memory now can be enabled within the host, across the host. You can make a decision for binding the memory, which is late binding decisions, where you, as you keep adding capacity or removing capacity or sharing the capacity. So there's a lot of good stuff that can come in from CXL, but along with that, there's a significant amount of software uplift that is required to enable this now. Now that you have choices, you have to go and define the solutions that are going to enable them for the applications. The solutions may come at a different level. You can have a kernel level changes that can hide it for make it transparent to the applications. There could be application level changes that you can say that I'm going to manage all that memory options at the user space and application level. This requires APIs for enabling within kernel, upside in the kernel. It requires orchestration for how we manage this memory, especially as we start going across pooling and start sharing it across devices and across hosts. So there is a lot of co-design required in this case. A lot of hardware-software co-design work that will be required. There will be devices that will be designed by hardware vendors. There will be systems that will be put together by system vendors. And there's going to be a solution. There's going to be stack that will be required in Linux and other open source, as well as internal development for product companies, where you need to make sure that we can optimize the resource utilization, we can create the right solutions and upstream them or make it available. And to make sure that we are achieving the goal that we talked about, that we'll optimize the platforms with least stranding that will make it more TCO and power friendly. So this is why this choice of having this hierarchical memory is important. Just quick plug in there, actually, this is why there is a work for this code design going on, not for standardization, but to make sure that how we put the solutions together within OCP under the group called software defined memory. So we are beginning to get together work in that area right now. Yes?
For hyperscale, obviously, the problem is not going to be, oh, we can't change our code to make this happen, right? There's no such thing as that. You just say, okay, we can't do what we want to do, throw resources at it. But there has to also be something that's reasonably easy to manage, to have sort of all the tweaks that you can do for, like, quote, normal sized projects. Because they're not going to want to, a lot of people are going to say, hey, I have a program already, I want it to run on this, a bunch of extra memory over there, that's great. Don't bother me with this, I don't want to make any changes. I know people only want to make like one line change to their program. Unfortunately, I'm quite familiar with that problem. So for you, it's great. You need all this stuff, but it has to be there have to be easy ways of doing this for the little people. So
Yeah, completely. Let me just quickly to repeat the comment is that hyperscalers have this need, they will be able to throw resources at it and make sure they get what, but how do you make sure that there's a larger community that can benefit from it, which is not necessarily going to be ready to invest to make such a big change, just for the mic. Yes, that is correct. And this is the reason why we are sharing it, because I think all of these technologies can thrive when there is a larger community. That creates a new solution, that creates the innovation. That's where it creates that, this is going to be long-term solutions, not just because what we put the resources right now and achieved our today's problem. Because if you really want it to be long-term solution, it has to be open community. So that's why we work hard to put it out there in the hardware perspective through OCP. That's why we are working hard to make sure that we bring it in SNIA and SDC so that larger community is involved. I don't know whether you wanted to add anything, Rita. Yes, that's a good point. Thank you. So taking it a little bit next step and see what CXL is doing. Essentially, what we talked about is that as memory needs are going faster, we want to make sure that we have the underlying memory technology options also, optionality provided to the applications. So tiered memory can allow us to do that where you have directly connected what we can call it as a near memory, like DDR4, 5, 6 as we go along. But at the same time, we are calling it far memory because as we look at CXL, you are making a trade-off. You're going to give a lot more optionality where you have different types of memories sitting behind it. You are going to look at, because of course it's going to be different interconnect, there is additional latency involved. And there's going to be, that's something that's going to offer you bandwidth trade-off too. Because as you can share a lot more capacity behind it, you are limited on a bandwidth here, or if you put a smaller capacity here, then perhaps you can match, but then of course it's going to limit on how much capacity you put. So there is a trade-off. There is a trade-off that you need the tiering to make sure. In the past, actually, we have been using for such tiering solutions, we have been using block storage today. Block storage definitely, as we'll talk through some of the use cases a little later, does add a trade-off. It does really give you significantly cheaper way of doing the memory expansion. It does require a significant change in applications or the intermediate tiers though. And so we'll talk a little bit about that. This gives us direct option without really making significant changes to the application. Again, not free, requires work, and that's what majority of the discussion is going to be. So the CXL memory tier is now where we see behind here that will allow us to do the performance and capacity trade-off. Let me jump back into the pyramid tier that we talked about. So now we can see that where we are introducing a new tier of memory now, which was a one contiguous tier of DRAM that is connected directly to the CPU, what we call as a near memory. Now we got this far memory where you make the choices. You can put smaller capacity and achieve the bandwidth extension you wanted because if you remember what we talked about, we have a limitation of how much we can put. Once I have 8 or 12 DIMM channels, then I'm going to put that many DIMMs on it. DDR channels, right? If you want to extend bandwidth beyond that, because the CPUs are growing in that capacity for number of cores as well as performance, we can achieve that by extending through CXL. If you wanted to achieve higher capacity and optimize the performance and TCO, we can add more capacity behind CXL, achieve the capacity memory where you are trading off the bandwidth, we are trading off the performance. For both of them, of course, you are adding latency. So you are making a latency trade-off in all of this. But this is the important thing that then this is load store interface. This is the key difference between what we are doing now, right? That this is not necessarily requiring me to go across PCIe or any other interconnect. It is more optimized on the cache line, the read writes. It's going to support now heterogeneous medium. So you can have different types of media, which we didn't have it, and we can scale it across multiple systems. We can create pooled storage. And most importantly, it is standard. And this is why we are here, that we can really grow the community by using these standard products. Now, as CXL, as we look future into CXL and bring it back to the hyperscale type servers, hyperscale infrastructure, we can see that actually, if I look at that, they really largely fall into these 4 pillars of types of servers. The whole reason for hyperscale to achieve the scale is really to make sure that we don't have too many types of servers. We just want to take small number of servers and deploy them at large scale, which is why we'll see that you'll few handful of compute SKUs, which are really driven by how much compute power we give, how much CPU they scale along with the cores that we provide or the core performance that we provide. Storage queues for large data warehouse and all those capacities we have talked about for storage as well as for databases. Now this is a large growing field for us, which is all the training and inference infrastructure. This is the huge amount of infrastructure investment that you will see happening in the industry. So if you take all these 4 types of servers, today all of them go with DDR4, and then as DDR5 starts getting deployed, all of them will deploy with DDR5. That's what CPU connected with. That's what we'll continue to deploy. HBM, of course, is as to the question that was asked, yes, this is where we are in the training and inference. This is where we get the maximum performance for GPUs and applications that require that high bandwidth memory. CXL plus DDR, the tiered memory, we see that actually they can definitely come into the compute and storage queues, storage where the databases and caching applications, as we talked about. And then inference is another area that we see that CXL can play a significant role. We will double click on some of these in the next few slides. This is exploration in the sense, what kind of capacity trade-off we can continue to do? What's the capacity performance trade? Yes, question?
Where are you in this? That's my, SDM is my, thing that I've been working for a long time. Where are you? Can you give us, I mean, obviously nothing secret, but can you just give us a general idea of
Sure.
where we are in that exploration?
Yeah, I mean, of course, it's exploration. So I can say that where the requirements are being driven, or identifying the applications that can live with significant performance capacity trade-off is how I look at it. Even though when we call it as a storage class memory, it's an interesting discussion where are we really trading that as a high performance storage, or is it more of a higher capacity memory, right? So this use case, we are really looking at from the more high capacity memory perspective. Ephemeral data, not persistent. And we see significant opportunity because some of the applications, as we start talking through, your choice is basically whether you want to increase the capacity of memory in the device or whether we scale out and go across the system. So we see there are applications like that which can benefit from it. Now, it's not a secret that this space of solution is pretty small right now, right? But I think as we allow these new technologies, because that has been the challenge, how do you really integrate into the existing platforms without really tied down into the small amount of non-standard interfaces? Now that we have those standard interface available through CXL, if we have the right capacity solution, high capacity solutions where we are ready to take even higher bandwidth capacity trade-off. This is where SCM theoretically can lie is my current understanding. Again, with a caveat that this is exploration right now. But we do see some use cases that can really survive bandwidth trade-off at a significant level. This is where, so I look at that, we have looked at SCM more of a higher tier of persistent storage like that. I look at it more from it's a kind of a lower tier of capacity memory, where you have really large capacity and low performance. Does that answer your question?
Yes.
Now let's come back, and we talked about the hardware options. Now let's look at what applications are those and what can use from there, right? What are ready to make that trade-off that we talked about for capacity and performance. So the caching, we'll go through the three types, the caching and databases, and then we'll talk about an inference. There is a area of training also that can benefit from, but I will focus on the inference for this discussion today. Caching is an interesting use case. It's a large amount of large use case for Meta, where we have caching solutions like Memcached sitting in front of the databases. This is crucially important for most of our applications to get the kind of performance they need, but at the same time make sure that we have the large databases at the back end growing without the need for continuously doing the higher performance for the whole database. So that's where the caching comes in. Now to achieve the higher queries per second that is required from the front end that is requesting this cache, it's important that we maintain the data for whatever we call it as a retention time, because that's where your cache is most effective. So for the platform where you are maintaining that data into memory, your choice is basically you have the large amount of memory to make sure that we maintain for that much of time to achieve the queries per second, and then make sure that you optimally utilize CPU. So the always challenge is balancing these two. At some point of time, if let's say your CPU can continue to support higher queries per second because of performance, if you didn't have enough memory, what it means is that at some point of time, you'll start wrapping around and drop the packets, right? So then for that, you'll make sure that you reduce the CPU usage to reduce the QPS, which means you scale out, which you land capacity. So this is why it's important that you need higher memory to optimally utilize CPU and make sure that you become CPU bound quickly, because that's where your optimal utilization will come. So it's important that we get the capacity or choice, otherwise you keep on going across and scale out. So the tiered memory solution is something that is important. We do have current solution which uses tiered memory with the DRAM plus NAND. By the way, we have Memcached and Memtier, of course, is out there in the open source community. We also have taken this tiered memory solution with the DRAM and NAND, which is cache lib, and the benchmarks that are tested for that are Cache Bench. Both of them are open source by Meta and are out there. This is what we use today, but it does require tiering for where you're accessing the memory, going to the block side accesses, which is a trade-off for performance, for latency. So it's not most optimal. You can continue to have higher CPU utilization, but not necessarily higher QPS, because you are going across accessing the block. So this is where it's clearly we are looking from moving from accesses to the PCIe devices to the DRAM. So you are ready to make the bandwidth trade-off already. Now cache lib is actually happening something at a user application level. Now when we look at CXL, and if the right kernel solutions come, it can happen really transparent to the application itself. Databases is where we really continue to, this is the back end of the caching solutions now, right? Here you want to really maintain a lot of persistent data, but the way to optimize that platform is to make sure that we land most SSD or most flash capacity on those. But to achieve the QPS expected for that much of capacity, you want to make sure you have enough block cache, enough mem table, which basically means memory. So if you provide that memory, there is a way you can add more storage that makes it more TCO positive across the infrastructure. Again, there is work that we look at, we saying that, can we make sure that that memory can be tiered memory and will allow us to maintain our QPS SLA from latency perspective as well as QPS perspective without making a significant trade-off on those, and allow me to increase the storage capacity. So the optimizing factor here is the storage capacity per node. And if I achieve that higher, then I achieve better efficiency across my infrastructure. So this is again place where we can look at if I can extend it with the CXL memory. Question?
Yeah, how the reason why load store would be better? I mean, the current drives, normal SSDs and stuff are all blocked, right?
Right.
So wouldn't you need an SSD or some storage device, sort of like SDM, in that you can at least read and I guess write, and there would be a back end to do the load stores that would require hardware changes to support that? I don't think CXL can magically make an SSD not require a block, right?
Right. So the question is basically for this kind of a solutions, do you need SCM kind of devices? Because how will CXL otherwise enable that kind of higher efficiency that we're talking? A good question. Yes. So essentially, what we're talking about is that if you see accessing the storage behind it, most of the time databases are holding your block cache and mem table in memory. The question is basically, if I increase that memory, I can increase the storage behind it. Now, question is basically, this increase in memory, does it have to be linearly increasing bandwidth along with the capacity, or is there a trade-off of having higher capacity at a lower bandwidth that allows me to make sure that I am not going to the SSDs all the time from QPS, especially for the read side. If the read side, if you are hitting that memory much more than you are hitting the backend storage, you are better off. And that's where you can make sure that the QPS, which is what the databases are serving on the front end, can we maintain that high? Can we make sure that my latency impact is not high? Because today what happens when the moment you get a miss on a block cache, you're going to go back into the SSD, right? And that's a significant hit. So if I can say that instead of going there, if there was a CXL attached DRAM, instead of DDR5 attached or DDR6 attached DRAM, yes, I'm going to pay latency to go to that device, but is it better than going to the NAND? That's the question. So that's really the area of exploration here. Right now, some of the experiments do show quite promise there. But of course, it has to be really managed at a scale and make sure that we have the solutions that are open and widely available for this. Inference is actually the significant area of opportunity here, because this really ties into the point that we talked about, that you're going to have a limit on a CPU, how many DRAM channels you can support. And this is where you're going to see that as we see into these inference platforms growing in capacity for number of GPUs or number of accelerators or number of processors that you're landing in there, there's a limit on how much memory that you can land in that system. Now, as we look at the GPU performance that is growing, as well as the number of features that feed into these GPUs for making the decision, both of these are growing, and the multiplication of these is what you need for memory for these platforms. So the capacity for a given platform is fast outpacing the capacity of memory that I can land in from the given number of channels. So how do we really expand the memory capacity for that is where these solutions will come, where we have a tiered solution. We do have currently, again, we do have solutions which look at expanding that with a DRAM plus NAND or DRAM plus SCM explorations. And we see that this is this is something that can benefit from having that CXL memory tier. This is the most promising area from these use cases also. So, yes, question.
How much does the application need to be aware of the tiers? And then you get software defined, which is trying to extract.
Yes. Yeah, so the question is basically how much applications need to be aware of this, and this is where you need to get into the more software-defined memory kind of abstractions. So that's a good question. It is actually, in any case, I think you need changes in that infrastructure. With where we do it and how we do it depends on what kind of flexibility you have in that infrastructure. The best, if you ask us, the best solution would be which will be transparent to the applications. That's the best thing. Now, the question is basically, how do you make them transparent? Do you make them in hardware or do you make them in software? Software makes it much more easy for us to go across all the infrastructure and makes it more portable across implementations. So it makes it much more standard. You get the right tier, and having them transparent to the applications means you really need to manage it in kernel somewhere. So that applications are really, and this is where you'll get into the most interesting part of the discussion as Reddy starts walking through that, which is right on time for the right question, because we'll give it to Reddy for taking it to the actual integrity of the work. Thank you.
All right. Okay, so I am going to focus mostly on the implementation side of the story. This includes primarily CXL 1.1, direct attached memory buffer. That will be the focus. I'm not going to talk about CXL 2.0 or 3.0, any one of that. So the goal is really to give you a flavor of, from a developer perspective, what are the things that are actually out there that you can actually take advantage of. And I will take two specific focus areas, broad focus areas. One of them is the Linux kernel tiering, and show you actually how the kernel tiering actually works behind the scenes. So it's a very detailed set of focus area. And then I'll also give you a flavor of, if you were to have tiering inside the application itself, I will take an example of CacheLib, which Manoj talked about, which is a very popular caching application used by Meta. And I will take an example of CacheLib, some of the work that is actually going on to implement the tiering within the application itself. So we see that these two things will evolve parallelly over the course of time, where if you really don't want to do any work, let the Linux kernel actually do the work, or it is Windows or VMware, the operating system doing all the grunt work, versus if you really need a fine-tuned way of actually doing the work, then it is an application-specific focus. With that, I'll try to do the demo if possible, but may not be feasible in the interest of time. So let me get into the actual mechanics of how you take the CXL buffer, attach it to the platform, what happens behind the scenes. So on Intel 4th Gen Xeon processor, which is called, codename is Sapphire Rapids, you probably might have heard about it. On this platform, we support type 2 device, CXL type 2 device. So CXL type 2 device actually provides .cache, .mem, .io protocols. And we use the .mem protocol as a way to enable CXL memory buffer functionality using type 2 flows. So the host firmware does a lot of grunt work. There are some setup knobs, and then the firmware itself has to go detect, is it a PCIe device or is it a CXL device? And you have to actually go through a stepwise training process to understand and learn what type of CXL device it is, what kind of protocols does it support. All those aspects have to be done through the firmware. Once that is actually completed, then you actually have to program the address decoders, because the CXL memory traffic is actually coming from the device itself, not from the host DRAM. So there has to be a routing. When the application says, I want to access the memory, it is fairly transparent to the application. But behind the scenes, there has to be address decoding flows that actually target the device itself. So there is a lot of that address decoding programming happens. The critical step is really the ACPI tables. ACPI tables essentially give you, are configured to convey the platform configuration aspects, performance attributes, and all that stuff to the operating system. So ACPI tables actually form a very critical component in the handshaking process with the operating system. There is a specific ACPI table I will cover. But before that, the operating system basically picks up all this configuration and then figures out what is the best way to configure the CXL memory. Broadly, CXL memory, there are two ways to consume. One, operating system can actually consume this transparently, just like host DRAM memory. No one has clue. The other aspect is operating system can create a device. If you have been exposed to Optane and PMEM, PMDK, there is a DAX device. So you can actually expose that as a DAX device. Then you can actually consume it directly through the application. Application controls everything using that flow, right? So there are two distinct ways of consuming. Now the critical component in this whole thing, when we talk about the tiering aspect, is there is a table called ACPI slit table. This essentially provides the details of the NUMA nodes, the distances among those nodes. So if you look at, this is the ACPI table, it talks about there are in a two-socket system, this is socket 0 memory, socket 1 memory, and this is the CXL buffer memory, number 2. And you can actually, the operating system picks this up, and you can actually see that in the Linux command line. The critical component in this is operating system uses this data as the fundamental backbone to really figure out when I have to take a piece of memory from the near memory, move it to the far memory, what is the best way to do that? And there is a node demotion list. So there is a demotion list for each one of these nodes, and it uses that as a way to demote the memory from higher level tier to the lower level tier. And that really forms the fundamental glue in the tiering process.
So,
yeah.
Presumably that means RDMA between tiers or something like that? Is that how you're going to do promotion and demotion?
RDMA,
Moving it between physical media?
you could, if you really want to, if the application can actually tolerate the latency, you can actually have that kind of plumbing too, even though we don't have that currently. Currently, most of the tiering is direct attached. With CXL 2.0, you will have a pooled tier memory behind the switch,
Well,
but nothing prevents you from.
The tiering that your partner showed, where you might have a fast and a slow tier out there on the CXL, does presumably mean that your promotions and demotions are literally physical copies.
Yes, exactly. Yep, absolutely. Sorry, the question is what does demotion mean? Is that the question? It's not a?
If it's not a copy. If it's not a copy.
Oh, it's not a copy. Well, demotion essentially means you have to copy the data from higher level tier to the lower level tier and invalidate and free up that space in the higher level tier. That's what demotion means. But it results in a copy, right? So unless it is a page cache and you can demote it and you can toss it out too as well. But depends on the type. Data is actually moving. Right, so there is nothing like you can just get rid of that and then free it out. Yes, yeah. The kernel uses that I'm trying to use the Linux kernel, the language more than anything else. Okay, so I kind of briefly covered. So here is the kernel tiering, left-hand side, and here is the application tiering. Sorry. Kernel tiering. Within the context of kernel tiering, what you are saying, the context behind the kernel tiering is everything, the data movement that includes the promotion aspect as well as the demotion aspect happens transparently via the kernel. In this case, we are talking about Linux kernel. If not, you can actually manage it through the application. So the key thing in the application space is that you need your own memory allocator. You have to manage the memory in the application itself, which is, you could potentially do that. There are applications and frameworks like Redis and CacheLib and so on, and all the database management systems do that too. You could potentially do that, but in general, there is a kernel tiering and there is an application way of consuming the data, and you could have the tiering in the application itself. So here is a click down of the kernel tiering. The fundamental to kernel tiering in Linux is that you have to understand how the memory is actually organized behind the scenes. If there is a concept of a node, and a node could have CPUs, cores attached as well as the memory attached. So socket 0, let's say socket 0 has cores and it has its own local memory. Socket 2 has cores and it has its own local memory in a dual socket system. And you have CXL based memory domains, which is essentially doesn't have any CPU attached. So there is a concept of CPU-less domains as well in Linux, and so is the case with the other operating systems too. Then behind, for each node, there are different zones available. I won't go into the details of each one of those zones, but the key thing is to look at the normal zone, which is the primary area where all the applications actually get, consume the memory in and out of. And each zone has watermarks, and this plays a very critical role from a tiering perspective. So there is a min watermark, low, high, and promo. When actually the memory amount of memory falls below the low, kernel swap daemon actually kicks in and tries to actually free up the space. And part of the freeing up the space is, shall I actually move that to the lower tier or not? And it is controlled by some of the configuration attributes, but in general, there is amount of free space that actually gets monitored, and then that actually triggers the freeing aspect from the higher level tier to the lower level tier, and there is a data movement aspect. And here is the placement aspect. So if you look at the initial, you have a lot of space in tier 0. So I'm talking about only one CPU here, just to give an example. So there is tier 0, node 0, and there is the CXL node. Initial allocation will everything go through the closest higher performing tier, which is the node 0. And then as it actually starts filling up and it actually crosses the low watermark, the pages actually move to the next level of tier, right? Both the freeing up the space goes to this tier, as well as the new page allocation also goes to this tier. Now this has a couple of implications. So now all of a sudden you have pages that are actually stranded in the lower tier, which is not really a high performing tier compared to the higher level tiers. And if you look at the all the new page and then when the swap daemon actually frees up the space, then you start allocating back again in the higher level tiers, right? So that's kind of the flow. And there are actually a bunch of statistics that actually show you how many pages have been migrated, how many pages actually attempted for migration, and so on. So the promotion aspect, now you have actually a bunch of pages stranded in the lower tier, and you need to be able to promote them, especially if they're hot. So there is a mechanism to actually promote them. There is a background process that routinely sweeps through all the pages in this lower tier, marks them as soft page fault. So it's a candidate for anytime a process tries to access that, it becomes a page fault, and then it gets swapped into the higher performing tier and essentially consume it from there onwards. So it's a mechanism to sweep through the lower tier data and mark each one of those pages. 256 MB is really the sweep that it does in one burst, and then it essentially does the page movement based on when there is a page fault, only if there is a page fault. Now, the memory, so you can actually control the page movement in different ways. So let's look at the page movement through the programmatically. So you can actually set the memory policy. So the memory policy essentially says, there are different ways of memory policies that you can program. So the default memory policy is you always allocate memory where the core is executing. So let's say if you're executing on socket 0 CPU core, you want to be able to allocate memory on the socket 0 host DRAM, that is the fastest memory. That's really the default policy. Or you can essentially say, no, I want a piece of memory, and then I want to allocate that piece of memory on this node all the time, right? So that is called binding. Then there is an interleaving thing where you are just interleaving among bunch of nodes. One-to-one interleave is what currently supported. And then there is a preferred option. I want to always allocate on this node, and if you don't have space, go to the other node, things like that. These things are actually programmatically controlled through the API. So if your application really wants that, you should use this part. If not, there is an admin control CPU set where you can actually control, administrator can actually control the allocation and the the NUMA memory node binding policies and all that stuff. And then there is a NUMA control that you can actually use to control the CPU nodes and the memory nodes and what you can actually consume from. So this is the most restrictive one. Your application may say that if NUMA control actually says, no, I want to allocate only from, application says I want 1 and 2, NUMA control says only 2, you get only 2, second node, nothing else. So it gets more and more restrictive. And then if you don't have anything else, if you don't have programmatic control, you have admin control, then its system default policy kicks in, which is allocate as close to the cores as possible. So there are a lot of details behind the scenes. I won't be able to cover that in the interest of time. Now, data movement is a very expensive part in general. Even if the kernel is actually doing the data movement, there is an element of compute capacity that you have to allocate to be able to move the data from one tier to the other tier. On Intel 4th Gen Xeon processor, there is an IP block called Data Streaming Accelerator that actually provides an offload capability. So which is called DSA, it essentially gives you a capability to move the data without actually consuming the CPU compute core capacity. So it's an offload capability, and it gives you there are 4 instances that you can actually have available on the Sapphire Rapids platform. Each one of them actually give 32 gigabytes per second in each direction throughput. So it's a fairly significant amount of throughput you can actually use to do the data movement. If you are familiar with the storage world, this is coming actually from the CBDMA world. So the Linux kernel page copy, you can actually use the traditional CPU page copy, or actually use the DMA offload page copy. This is being worked out, still not available in the upstream kernel. Currently, there are a lot of POCs going on to figure out what is the best way to integrate into the kernel so that we can actually take advantage of the IP offload capability as well. Okay, so quickly, so I kind of briefly covered the Linux kernel tiering internals. I had to speed it up primarily because of lack of time. If there are questions, I can address maybe after covering this one.
Question on the product slide.
Yeah.
Are there specific applications that are now taking advantage of the migrate pages, move pages functions? Specific, like not an SAP HANA, but like something like the databases and all.
Yeah, there are a few frameworks that actually do take advantage of that. Yeah, exactly. There are. But it's not like standard off-the-shelf application can't really use that. But yeah, there are a few frameworks that do take advantage of that. Great question, by the way. So application tiering. So I kind of talked about the Linux tiering. Application tiering is CacheLib essentially has, like Manoj said, we don't have, CacheLib has one tier called memory tier. The other tier is a block tier. We are currently working on actually having multiple memory tiers. So you have a flexibility when you want to deploy, you can actually take advantage of the CacheLib to do the deployment with, one is a host DRAM tier, the other one can be a CXL tier. So you can actually do the data migration between those two. So that work is in progress, and we expect this to be available in probably in this year pretty much, that activity. And here is the click down of how the memory tiering works within the context of CacheLib. CacheLib uses something called internal memory allocator called slab allocator. It allocates the memory. There is no everything. The memory allocator is completely in-house within the CacheLib itself. Slab allocator actually plays a critical role. So a slab is essentially a big chunk of contiguous memory, physical memory. So 4 MB in this case. And then it actually organizes this into a bunch of memory pools. Memory pool is basically an abstraction that you can actually fine-tune the allocation part. And then you have the allocation classes within the memory pool. Allocation class is every size. Let's say you have 256 bytes, that is one allocation class. 512 bytes, that's a different allocation class. So that when it comes to freeing up the space and everything, you are not consuming a lot of cycles to free up and allocate the memory. So it uses the allocation class as the abstraction for easing the allocation and improving the throughput aspect of that. So that the migration aspect happens. This is let's say this is the memory tier and this is the DRAM tier. You can actually see that when there is essentially a data migration, it moves from one allocation class to the other allocation class in the lower tier. And the promotion happens in the same way too. And we are looking at, and here is the click down of the what happens when there is a need for eviction. So the background evictor actually kicks in. There is an LRU list for each class, and it looks at all the stale items, moves them into the lower level tier, again through the background evictor. And here is the solution. So we have actually tested this for the last 1 year or so. We have been testing quite a bit. Cache bench application on the Intel 4th generation processor using the Intel FPGA card. This is a pre-production card, CXL memory buffer card. So there is a lot of work that has happened, and essentially we are ready in general from a solution perspective for the caching type of applications. So summary, like Manoj said, we are actually doing this work. As you know, the tiering work as well as the application tiering work requires quite a bit of coordination with device vendors, operating system vendors, and ultimately the consumers, which is hyperscalers. We all need to come together as a way to figure out the best way to deliver a scalable solutions. Like your point was, it's not really solving hyperscaler point solutions. The goal is to solve the solutions that are actually scalable for the broad market. So that is really the focus behind the OCP SDM initiative. And we are looking at all different areas. So interconnects, devices, the attributes, what are the thermal, mechanical, interconnect, the form factor type of attributes we need for mass deployment. And then the software area, the tiering aspect within the software we have to cover. This includes Linux. Even though I covered Linux, we are working with VMware and Windows team as well. So there is a participation from OS vendors in this community. And the goal is really to broaden the CXL-based solutions for the broad market, starting with hyperscalers consuming them, but essentially broaden it out to the broad outreach for the broad market. We request you to actually consider joining the software-defined memory working group. It's an opportunity for you to bring in your perspective and influence the overall, the broad, scale opportunity. With that, I guess I'm out of time, so I skipped demo. My apologies, but any questions, maybe? Yeah.
One of the drawings that you showed there was that the CXL attached memory would be a Type 2 device. One of the chairman in JEDEC and all of the vectors in JEDEC are that we're going Type 3 for CXL memory expansion. I don't think that changes this picture, does it?
No, it doesn't. So the Type 1, Type 2, Type 3 is a bit confusing. So Type 3 basically says it is a .mem protocol, CXL .mem protocol. Right? .io is common to all of them, but when it comes to the data plane protocol, .mem is the Type 3 specific, and then Type 2 has .cache and .mem. So you can always deliver a memory buffer using Type 2. The only thing is the device basically says when there is a .cache protocol coming from the platform, says I don't have this cache line. So it's a no data response.
Not cacheable.
Yeah, exactly. Yeah, exactly.
That's the only difference.
That's the only difference. That's the only difference. Yep. Yeah.
The goal of it, it seems like all this stuff has to be time integrated into the kernel OS and Linux. I assume this is all being pushed upstream or into the Linux.
Yes. Yeah. Most of the stuff I covered in the Linux kernel thing, it's already there in the upstream. So if you pull in 5.19 as an example or 6.0, you get that functionality. But there are still some, things that are still being worked out. So things like the demotion aspect of that, kernel does not care about your memory policies in the application. It just ignores that completely. So there is a patchwork that is going on. Some of the node demotion list doesn't work very well in the dual socket. Even if you have a CXL buffer on the second socket, the demotion thinks only it is from first socket. So it cannot demote from the first socket host DRAM to the CXL buffer attached to the second socket. So there are a bunch of things that still need to be sorted out, but whatever I talked, pretty much they are in the upstream. There are.
It also implies software-defined, implies a virtualization layer and background movement, all that kind of stuff. This seems more like a caching.
Yeah, this one is like a bare metal focus, but in the SDM, we are talking about containerized, what do we do? And we have virtual machines, what do we do? So that focus is also there, but in the interest of time, we could not cover those things as well. But the goal is to do the virtualization. Yeah, we are starting from the ground up and then going up. Yeah. Any other questions? Yeah. Excellent question. So the question is there a plan to incorporate byte interface SSD? It really depends on the device, vendor ecosystem. So you probably heard some couple of announcements in the Flash Memory Summit, where you can actually take the NVMe controller. You can actually create a CXL controller on top of that. Of course, you need a lot of integration aspects, and then you can actually create a load store semantics through that. And then, of course, CXL 2.0 actually gives you the persistence aspect of that too for the load store if you really want to take advantage of that. So looks like there is a good amount of traction in that space. We'll have to see which ones will come to the market. But yeah, absolutely, it's feasible. But you have to worry about block semantics like 4K bytes versus cache line semantics. We are dealing with 64 bytes at any given time. There is a latency implications. Somewhere you need to buffer that through the the DRAM inside the drive. So you have to do a lot of acrobatic work to get it right. Yeah. Any other questions? Thank you for your time.